Hi, hello everyone. My name is Vivek. I am a software developer. I make videos about containers, Kubernetes, Go as a programming language, distributed systems, and sometimes about software engineering in general. So if you have been liking the kinds of videos that I make, you should consider subscribing to the channel. In this particular video, I'm going to start writing an aggregated API server. But before actually doing that, we will briefly talk about what exactly are aggregated API servers, Kubernetes aggregated API servers. Are there any alternatives? And why would someone want to write their own aggregated API server? And then I would actually start implementing the aggregated API server from scratch in this same video. So if you have watched my previous videos, you might know that uh, we can introduce some custom resources in our Kubernetes cluster. So let's say you have some use case and the resources that are already available in the Kubernetes system, the standard Kubernetes resources are not able to fulfill your requirements, are not able to, let's say, satisfy your use case, the use case that you have. In that case, what you can do is you can introduce new resources to your Kubernetes cluster using this construct called custom resource definition. So you can create custom resource definition to introduce new kind of resources to your Kubernetes cluster. So that is, let's say, one way of introducing new resources to your Kubernetes cluster. And aggregated API servers are, let's say, different ways or a second way of introducing Kubernetes resources, new Kubernetes resources to your cluster, I would say. So now we are going to actually talk about what exactly are the limitation of CRDs way of introducing the resources, and because of that, people might want to use aggregated API servers. I have a video already where I talked about the comparison between CRDs and aggregated API servers. So I highly recommend you checking that out. But because it has already been some time for that video, I would very briefly talk about the differences, the comparison, and then we would obviously deep down to deep dive dive deep to actually writing the aggregated API server. So like I said, when you introduce the resources using CRDs, the resources or the requests that you make for those resources, let's say we introduce a resource called cluster. I already have a video again about this. There is this project called cluster that I made, and that's why I'm taking that example. So let's say you introduce this resource. Whenever you interact with this resource that is introduced via CRDs, you are still talking to the main Kubernetes API server, and the data is still stored in the same etcd storage where the standard Kubernetes resources are stored. So this is one kind of limitation, I would say, because if you introduced a new resource and that is going to be created by the users a lot, in that case, there are chances that you might, let's say, affect the performance of API server, because like I said, the resources that are created or introduced by CRDs are still going to be served by the main API server, and they are going to get stored in the same etcd backend. Again, I have talked about it already in one of the previous videos. I would link that somewhere in the video, in this video. The other difference that I would like to talk about is the protobuf support in case of aggregated API servers. So let's say the resources that are introduced by CRDs, they don't actually support protobuf as a communication medium. Let's very briefly talk about protobuf. So you know that there are some other ways, for example, let's say JSON and YAML, to marshal your data so that data can be transferred between the components, between the entities, and then things like that. So whenever you want to, let's say transfer some data, you would marshal that into JSON or YAML. Similarly, protobuf is another kind of, let's say, medium to encode your data. And this is, I would say, this is lighter, easier, and because it's easier and lighter, it's less heavy on the system where this marshalling and unmarshalling is going to happen. So for example, let's say you have API server deployed on a machine, and you have, let's say, tens of thousands of resources. If those resources are served by API server, they are going to get converted to JSON, and that would be a resource heavy operation. But if you introduced the resource in such a way that it supports protobuf, in that case, because protobuf is a lighter, let's say, mechanism, it's a binary data, the conversion is going to be the encoding, the marshalling is not going to be that heavy on your machine. And protobuf is only supported for, let's say, standard resources, and it's not supported by the resources that are introduced by CRD. So this is another benefit. If we write the aggregated API server and we introduced a resource called, let's say, cluster, using that aggregated API server, we can add protobuf support into this resource. And every communication that happens between the Kubernetes components for standard resources, that happens using protobuf. So for example, let's say if kubelet asks for a resource from API server, hypothetically, in that case, kubelet would explicitly set the header and ask that I want this response to be in protobuf format. I don't want the JSON data. And the reason, like I said, is because protobuf is lighter and it's not resource heavy on your machine. So let's very quickly go ahead, and I will try to show you what exactly, how do we interact with, let's say, protobuf data. So like we see here, we already have a Kubernetes cluster that I just created. And if I try to, let's say, get Kubernetes pods, so kubectl get pods, and so this is the endpoint that is getting called. I want to actually interact with the endpoint, and that is the reason I changed the verbosity API v1 namespaces default / pods. And then I want to explicitly say that give me the protobuf data. So this is the header that we can add, and it's a protobuf. So we are going to pipe it to hex dump and -c. And if you see here now, obviously it's a binary data, so we are not able to read it. But as you can see, it properly returned pod v1.pod list. If you see here, it means that we are able to communicate, at least for pods resources, using protobuf. But if we try to do the same for the resources that are introduced via CRDs, we will not be able to do that. So if I try to list CRDs, we don't have any CRDs right now. So let's go ahead and create this CRD very quickly in our Kubernetes system, so that we can try to interact with that. So I created the CRD. It means that we have introduced a new resource. So cron tabs, and similarly, I would like to know the API that is being called here, if you see. And let's do the same again. So I'm going to try to get the cron tabs, the resource that I just introduced using CRDs, and then I will specifically ask for protobuf, and let's see what it says. So 8001, and then APIs table.example.com v1 namespaces default, and then cron tabs. And then I'm going to add the same header to explicitly ask for the protobuf response. And like you see, it clearly states that failure, only the following media types, only the following media types are accepted: application JSON, application YAML, application Kubernetes protobuf is not acceptable. So this is what I meant when I said when I said the resources that are introduced by CRDs don't support protobuf, but the standard Kubernetes resources or the resources that are supported by supported by main API server or aggregated API server, they support protobuf. The other difference between CRD's ways of introducing the resource and aggregated API server is sub-resources. So you might know about some sub-resources. For example, let's say status, scale, these are some of the sub-resources. Exec, logs, these are all sub-resources. These two sub-resources are for standard Kubernetes resources for pod, and these two are supported for standard as well as custom resource ones. So if you introduce the resource using CRD, these two are the only resources. Scale and status are the only two resources that are sub resources that are going to be supported. You cannot have any sub-resource other than status and scale for that resource that is introduced via CRDs. But for the resources that are served via via your aggregated API server, you can have any number of, let's say, sub-resources. For example, uh, let's say, yeah, I mean, logs for the pod resource is another example, right? Similarly, exec is another example for the pods resource. The other difference that I would like to highlight between CRDs or resources that are introduced via CRDs and the resources that are served via API server, main API server or aggregated API server, is graceful deletion. So in case of let's say some of the resources, not all the resources, but in case of some of the resources, Kubernetes API server supports graceful deletion. What that means is when you run the delete command for a particular resource, if there are some other backend resources that you would like to clean up, that is automatically implicitly supported in case of the resources that are served by introduced by or served by, let's say, main API server or aggregated API server. In case of CRDs, we can achieve the same using finalizers and reading the metadata field deletion, graceful deletion timestamp, but it's easier in case of aggregated API server, but I'm not going to say that it's not achievable in case of CRDs. Resource cohabitation is another thing that I have already talked about. In case of CRDs, in case of, let's say, the resources that are served by introduced by main API server, one resource can live in multiple groups. If you remember, I think deployments, not deployment, but I think ingresses were part of extensions, and then extensions group and networking group at the same time. So yeah, it's pretty common in case of the resources that are introduced by main API server, and we can achieve the same using aggregated API server. So these were kind of some of the, let's say, differences between the aggregated API server resources that are introduced by aggregated API server and the resources that are introduced by CRDs. Now, so yeah, I mean, I think the only kind of reason here that I see to, let's say, use aggregated API server is uh, maybe if you think that your resource that you want to introduce is going to get created a lot. In that case, like I said, it might be resource heavy, it might affect the performance of main API server. That is the kind of and obviously the protobuf. Those are some of the reasons because of which you might want to consider aggregated API server to introduce your resource. There are some other kind of differences, for example, in case of aggregated API server, because you are in a way writing your own API server like the main API server. You can achieve a lot of things. You can validate the data before, yeah, it's before actually it's stored in etcd and then things like that. So you will not have to kind of make a call to the webhook service and things like that. So that's another benefit. Now let's go ahead and look into what exactly are we going to build in this particular video. So if you remember, again, if you have watched my previous videos, I created this project called cluster, and what this project does is it introduces a Kubernetes resource called cluster using the CRDs. So using CRDs, it introduces a Kubernetes resource called cluster. And when you create a cluster resource in your, let's say, local Kubernetes cluster, an actual managed Kubernetes cluster is spinned up or created in DigitalOcean. So this is what this project used to do, or does. And what we would like to do is we would like to do the exact same thing using aggregated API servers. So we are going to, let's say, introduce the same resource, but we will do it using aggregated API servers and not using CRDs. So yeah, let's go ahead and start doing that. But before actually writing the code, I would like to again very briefly highlight or define aggregated API server. So like I said, there are two main ways of, let's say, introducing new resources to your Kubernetes cluster. One is CRDs and another one is aggregated API servers. Using aggregated API servers, you are, let's say, writing a new API server like the main Kubernetes API server. So this server is going to be deployed on your Kubernetes cluster along with your main API server, and then main API server is going to know about your aggregated API server, so that the resources that are served by your custom API server, or let's say, so that the requests for the resources that are served by your API server can be proxied to the custom API server from the main API server. So I'm going to talk about these things in much more detail when we go through the rest of the video. But for now, we can assume that we aggregated API servers are, let's say, API servers like domain Kubernetes API servers that introduce the new Kubernetes resources. And we tell the main Kubernetes, so we have, let's say, main Kubernetes API server, and then we have aggregated API server, and then we tell main Kubernetes API server about the aggregated API server using this resource called API Servers. So when we create the API service resource, main Kubernetes API server basically the knows which group is served by the aggregated API server. So when you try to interact with, so let's say it introduces a resource called cluster in the group viveksingh.dev. And when you create the API service resource, you are going to tell the exact same thing to the API service resource, that in this particular group, and let's say in this particular version, there is this resource that is served, that is introduced by aggregated API server. So whenever main Kubernetes API server receives a request for cluster resource under this version and group, it would know that it has to proxy that request to the aggregated API server. And we are going to look into the architecture in more detail in just a bit. But this is what Kubernetes aggregated API server is. So let's go ahead, and I am going to follow this book called Programming Kubernetes throughout throughout this series. And if you see here, this is how the aggregated API server looks like. But before actually looking into that, I'm going to show you the main API server. So this is, if you see, this is how Cube API server looks like. And after the handler chain, the request comes from here. And after the handler chain, there is this component called Cube Aggregator. And Cube Aggregator looks into the request and it figures out if this request should be handled by the main API server, or this request should be proxied or forwarded to the aggregated API server that we are going to write. And this Cube aggregator knows about or gets to know about the resources that are handled by aggregated API servers using the API service resource that I just talked about. So this API service resource that we create. So we are going to look into all of these things in very much more detail while I go through the implementation, and you can refer the older video as well where I talked about CRDs and aggregated API servers in much more detail. So let's go ahead and let's start implementing that. So like I said, we are going to write a new project called Cluster API, and that project is going to basically be an aggregated API server that is going to do the exact same thing that is done by this project. That is, it will introduce a new resource called cluster, and if an instance of that resource is created, a respective DigitalOcean Kubernetes cluster would be created. And we would start with very small, and we would keep adding things to that aggregated API server. So let's go ahead and create a directory called cluster-API and cd into cluster-API, and let's open our text editor there. And before actually going ahead and starting to implement the code, let's go ahead and talk about one more thing. So whenever we talk about Kubernetes resources, again, I have talked about this in some of my previous videos, but I can briefly explain again. So whenever we introduce a resource called, let's say, called cluster, the resources live inside group and version. So let's say it is going to be in v1 alpha 1. So cluster is a resource that we are going to introduce, and this resource is going to be in group vvxing.dev, and the version is going to be v1 alpha 1. Now let's say in future, if we want to introduce a new version of the resource called v1 beta 1, in that case we would have two versions of the same resource cluster, and in that case there should be the conversion between these two versions should be easily possible. And it's not just about two versions. In future we can have another version called, let's say, v1 beta 2, and again, when we have three versions, we should be able to convert between these three versions without any issues easily. So to facilitate that, what, let's say, Kubernetes recommends is they follow hub and spoke model. What hub and spoke model is you have one central version. Let's say in Kubernetes terminology, we call it internal version. So we have internal version, and once you have the internal version, what you're going to do is to convert, let's say, any of these resources to the other one, you would first convert it to the internal version. So let's say you have to convert v1 alpha 1 to v1 beta 2. What you would do is you would convert v1 alpha 1 to internal version first. So let's say our use case is to convert v1 alpha 1 to v1 beta 2. In that case, what this would result into is v1 alpha 1 would be converted into internal version first, and then internal would be converted to to v1 beta 2, and this would basically make things easier, because the conversion only kind of the conversion logic only needs to know about, if we go with this particular algorithm, the conversion logic would just need to know about how to convert itself to the internal version and from internal version. So for example, if v1 alpha 1 knows how it can convert itself to the internal version, and how an internal version can be converted into one v1 alpha 1, if all the resources have this knowledge, we can easily convert any version of resource to any version of resource. I hope that makes sense. But if we were not following hub, and so in this particular case, internal version is the hub and other version are the spokes around this hub. And this is explained very well in this programming Kubernetes book as well. So if you see here, we have internal version and we have these three versions that are spokes. And if v1 needs to get converted into v1 beta 1, we can convert it to internal version, and then internal version can easily be converted to v1 beta 1. If we did not have hub and spoke model, I would maybe leave it up to you to figure out how challenging would things get, because if we did not have hub version, in that case v1 alpha 1 would need to know how to convert to v1 beta 1 and v1 beta 2 and vice versa. So this would become very kind of complex matrix like scenario. So for now, for the resource that we are going to introduce, in that resource we are just going to introduce one version, v1 alpha 1, but in future we are going to add other versions because we would actually like to see this conversion and things like that. So yeah, I just wanted to talk about this hub and spoke model that is very important, I would say. The other thing that I would like to talk about is, uh, I think I briefly mentioned the architecture of main Kubernetes API server, uh, where we have the aggregation layer, and that aggregation layer, just by looking at the API service resource. So using API service resource, we register our aggregated API server to the main API server, and using that API service resource, aggregation layer or kube aggregator that is part of main API server figures out what are the groups that are supported, that are served by which API, which aggregated API service, let's say. Once the request gets to the if you see here, once the request gets to the custom API server, this is the kind of architecture of custom API server. And before actually moving forward, the other thing that I would like to highlight is, if you see here, all these versions. So let's say I would also like to talk about this thing called internal version, and how the core logic of the aggregated API server is only implemented for internal version. So let's say your resource is served by two versions, and those two versions are v1 and v2. So you have two versions of your resource, and let's say the request for v1 comes from the user, and if you see, the conversion happens to the internal version here, and the main logic, if you see here, int here means internal version. So the v1 gets converted to internal version, and main Kubernetes logic is implemented only for the internal version. And whenever, let's say, the external versions are required, they are changed accordingly. So for example, if I have configured that the storage version among v1 and v2 is v2, then if you see here, from internal version, before actually storing the things to etcd, it gets converted to v2, and then it gets stored in the etcd. So what I'm trying to highlight is, doesn't really matter how many external versions you have for your resource, or it doesn't really matter how many versions your resource is supported in. The internal logic of the aggregated API server is going to be kind of implemented only for the internal version, and wherever required, that internal version is going to get converted to the external versions. The other thing that I would like to highlight is there is this thing called delegated authentication and authorization. Again, I have talked about it in one of my previous videos. What happens is once the request comes to the aggregated API server, the aggregated API server, because it can easily assume, the aggregated API server can assume with certainty that there is main Kubernetes API server. So this can delegate some of the things to the main API server, and those things are authentication and authorization. So whenever a request comes in, it uses the resources called token review and subject access review to actually authenticate and authorize that request using main API server. So yeah, I think this is uh, this is what I wanted to kind of explain before actually we get to implementing the API server. So let's just go ahead and start writing the code. And like I said, uh, this is the this is the API that we are going to introduce. So let's just go ahead and use the same kind of the types struct that we have for the cluster resource. So I'm just going to copy. I'm going to create the same directory structure here. So make that directory package APIs cluster and v1 alpha 1, and then I am going to cd into that, and I would just kind of copy these files. I will show these files to you, and it would make sense because I have already talked about these in one of the videos. So this is types.go, and I'm also going to copy doc.go, and then register.go. All right. So here we have types.go, and like I said, we are going to introduce this resource cluster. I also recommend maybe watching this playlist that I have linked here. This would give you kind of good understanding of what exactly these files are, and why do we have this type in this particular way. So I think I'm going to maybe explain this briefly, but if you watch that YouTube playlist, things would be clearer to you. So I'm just creating some Go types, and these types are going to be basically eventually get converted into the Kubernetes resource. So we have cluster and we have cluster spec. Under cluster spec, we have name, reason, version, token, secret, because these are the things that are required to, let's say, create Kubernetes cluster on DigitalOcean. I'm going to remove these things, cube builder related things from here, because we don't really need cube builder, and but we do need we would need open API. So Kate's open API gen, and it is going to be true. And we will talk about why do we really need open API gen for these types. But yeah, briefly, let's say the main API server gets to know a lot about this new resource that you are introducing using aggregated API server, using the open API spec that you kind of provide to the main API server. Does that make sense? So you have aggregated API server that introduces some resources. Those resources are these resources, and main API server needs to know about, let's say, schema of these resources, and that is the reason open API gen is required here. And I'm also going to add the conversion. So conversion then, and I'm going to specify the package where the versions are present. So the conversion is going to, if we again talk about the hub and spoke, we would have to have the conversion logic from external version, that is, let's say, v1 alpha 1 to internal version, and that's what we are going to generate using code generator. Okay, so our types, internal and external types, are going to be here. That is the reason we have specified that path here. And we have we need deep copies in, we need open API, we need client sets. I think we are good. Let's go ahead and try to create the respective files for the internal type. So uh, by standard, under v1 alpha 1 we are going to have the external types, and under just cluster we are going to have the internal type. So for internal types we don't really need anything, we just need the deep copy, and that is the reason I'm just going to have the deep copy, and I would remove everything else. We would also need to remove or change the package name here. Okay, so now again, this might make a little more sense to you once you have watched this playlist. But what we are doing is, if we talk about that resource living in group and version, we are just trying to kind of create the schema of the resource that is going to be introduced by our aggregated API server, and this is how the schema of that kind of resource looks like. That's pretty much it, I would say. And we have created two copies of the same files, because like I said, we have to have two versions at least: the external version using which the users are going to interact with the resource, and the internal version on which the main aggregated API server logic is going to get implemented. This is because we have not initialized a Go project yet. And let's go ahead and do that. So we have a Go project now, and we are seeing these errors because we are trying to register these resources are as known types, and they don't satisfy some implementations. So let's go ahead and try to generate the code for these types. So I'm not going to write the code generation logic, commands here. I'm just gonna create a folder called hack, and here we are going to have a new file called generate code.sh. And again, what we are going to do is, like explained or like configured here, we are going to generate some code for these types. Those that and that those yeah, that generated code is required to, let's say, interact with these resources. And like I said, one example is obviously open APIs in. And so we are going to I'm going to copy this code from here. And then what we will do is we will go ahead and just run this. So if you see here, what we are doing is we have these many generators. These are upstream generators, client gen, lister gen, informer, deep copy gen, conversion gen, and open API gen, right? So we are just calling these kind of modules, let's say, to generate the respective code, and that code is going to get, let's say, generated in this particular directory. This also needs a boilerplate file. So let's go ahead and create that file, and let's say we are going to say generated, or let's just copy it from somewhere. So this is what is expected, let's say. All right, so now that we have our kind of schema defined and we have the generate code.sh, I would obviously push this file, so don't worry about it. Let's go ahead and try to generate it. So we will have to make the file executable first, and then generate code.sh. So it's generating client set lister. Okay, informers, deep copy functions, conversion, and open API. If we go ahead and look into, okay, so if you see here, a lot of these things have been generated, and this is what we wanted to generate basically. And we see some issues there, and the reason is local scheme builder dot register, the conversion functions that we have generated are registered using the scheme builder, and our local scheme builder is called scheme builder. So let's just change local scheme builder to what we have. Okay, so now it looks like the code compiles. Now let's just go ahead and start. This was kind of, let's say, this was part of scaffolding the project. We did not really do anything here. And now we are going to actually write the code. So before actually doing that, let's talk about a pattern that is used by the main API server, even main Kubernetes API server, to write the server. So it's called options and config pattern. So what happens is you have a type called, let's say, options, and then that type is converted into another type called config. So what exactly is the difference between options and config? So when you want to, eventually the aggregated API server that we are going to write, it is just a binary, and when that binary is run, providing some of the details. When I say some of the details, what I mean is it would accept, let's say, etcd server endpoint, right? So let's say hyphen etcd endpoints. It might also accept kubeconfig file path. It might also accept verbosity of the logs and things like that, right? So these are the options that I would want my API server to accept, and these are the options that we are going to have in the options type. We are going to implement it in just a second, but before actually doing that, I wanted to kind of briefly talk about this. So all of these things are going to be inside options. So these type value are, so value here is just going to be, let's say, concrete values. So here, let's say, it's going to be locally running etcd, so something something something, right? Kubeconfig is going to be again a string that is going to give you the path of the kubeconfig file. These are standard values. They are not, let's say, live connection or anything like that. They are not runnable in a way. Does that make sense? When we convert this option to config, what we mean is now etcd, if we have etcd here, it's actually a connection to the etcd. So we can use this to maybe write and read things from the etcd. So this is the main difference between options and config, and this is the kind of main building block of the aggregated API server. I hope that makes sense, and if not, we are going to look into that in a bit more detail, and then it might make more sense then, I would say. So yeah, once we have config, we can basically have completed config, and completed config is nothing but you have config, and then you can have default values. Add default values to the config and you would get completed config. And once you have completed config, there is this function called new on completed config that gives us the API server, and this is the API server that can then be run to actually run your API server. So this is exactly what we are going to implement right now. So let's go ahead and refer this book that we have been kind of talking about. And we are going to follow this particular heading called Writing Custom API Servers. And we are going to very heavily use this library called kates.io/API server. And this is the same library that is used by the main Kubernetes API server. So let's go ahead, and this is the option and config pattern that I just talked about. So I'm going to create a new folder here under package, and let's call it server. And under server, we are going to have a new file called options.go. And under options.go, we are going to have the options and other things that we just talked about. So we are going to have an options struct called, let's say, cluster server options, and it's going to be a struct. And this is the same thing that we talked about here, this particular type that I just talked about. And it is going to have some let's say flags, some options that we can accept, because like I said, our aggregated API server eventually is just a program, a command line tool that is run, and it accepts some values from the flags. So there are some recommended options by API server, and we are just going to leverage those so that we don't have to really do a lot of manual work. So let's go ahead and call them recommended options, and then let's call it generic options, and here we go. And we will obviously have to kind of import that. And now we have this option. And once we have the option struct here, let's go ahead and write a new function that would give us the cluster server options. So func new cluster server options, and it is going to give us the cluster server options. Like I said, we need this because from cluster server options, we are going to create the config, and that is the reason we have this kind of, let's say, constructor, for the lack of better words. So out, error out, and then it's going to be writer, and it returns cluster server options. And recommended options are, let's say, again, it can easily be initialized using generic options dot new recommended options. and we are going to have prefix here. So let's have a variable called default etcd path prefix, and it's going to be registry tweaksing.dev. And then we are going to have, we need to pass runtime.codec. Before we actually pass this, let's go ahead and so let's talk about what exactly is this codec here, right? So what happens is when we have a type and we want to store that type into the storage backend, let's say etcd in our case, the kind of serialization needs to happen. And to facilitate that and to kind of configure which particular version the serialization should happen, we configure the codec. And to configure that, we are going to create a scheme so that we can then initialize the codec. So let's create a file called scheme.go, and here we are going to have scheme. So again, I have talked about these things in one of the previous videos, but if I try to briefly explain, when you are introducing a new type to the Kubernetes, you have to register that type into the scheme. Scheme is basically, let's say, a kind of map between which particular type are introduced and what is the respective go type and things like that. So if scheme doesn't have your go type and someone tries to interact with that resource, it would simply complain and say that, I mean, the server doesn't know about this type. So that's what the scheme is. So we are just initializing the scheme right now. We are not registering any type into the scheme. We will have to do that, but I'm going to do that later. So runtime.new scheme, and then we are going to create the codec, and codec is going to be so serializer.new codec factory, and then scheme. If you see here, if you see the kind of definition of new codec factory, it provides methods for retrieving serializers for the supported wire formats. And this is what we basically mean. So using this codec, we can call a method to kind of get the serializer. So let's go ahead and use that codec dot legacy codec, and then we pass the version on which we want. Let's say we want to configure this particular version to be to the storage version right now. So let's say we have our resource right now, we just have v1 alpha 1, but if we are supporting multiple versions of the resource, this is the version using which the resource would be stored in etcd, or in other words, this is how we are configuring the storage version of the resource. And we are going to say v1 alpha 1 dot scheme group version. And now if you see, it basically returns the so we have the options, type that we talked about here. I would like to go ahead and talk about this new recommended options. This is kind of the not most, but one of the most important pieces here. So to have the options type, we introduced, if you see here, one type that just wraps the recommended options. We could have, if we want to, we can have another types here, another fields here. On the book, we have shared in form of factory. We might introduce that later, but right now we don't need that. And this is initialized by default for us from upstream server options library. And if you see here, etcd basically kind of decides which storage backend do you want to use. Secure serving, this configures the delegated authentication. I think I briefly talked about delegated authentication. Once the request has been received by the aggregated API server from the main API server, aggregated API server would like to kind of do additional check by contacting the main API server, and that's what delegated authentication is, delegated authorization, and all of these things are kind of, let's say, initialized for us, right? And once we have the recommended options, we are going to look into add flags, etc. Later. So we have the options. Now what we are going to do is we are going to create the config. Again, if we refer this particular rough diagram here, from options we are going to have the config, and config is the real kind of deal here. Config is going to have the runnable, let's say, data structure. So I'm going to create a new file called config.gov, and this is in server package. And like options, we are also going to create types for config. So type, and then let's call it cluster config struct, and it's just going to have the kind of like recommended option, we are going to have recommended config. So generic config, and it's going to have recommended config. And again, let's call it generic API server, generic API server. And we can have another field here if required, but for now, like I said, I'm just going to kind of, let's say, make the smallest aggregated API server possible, just so that we can run it and we can see what exactly is happening. So we have the config type, and once we have the config type, what we can do is we can go ahead and we can write this function here called config on cluster server options, that is going to give us the cluster config. So it's going to be on cluster server options called config, and it's going to give us cluster config and then error. And to do that, what we are going to do is we are going to call k dot recommended options dot secure serving dot maybe default with self-signed certs. What it does is, if you look into the, it doesn't have the comments, but it generates the self-signed certificates using which basically you have to provide the respective certificates to kind of communicate with this aggregated API server that you are writing. So those are the certificates that are generated by maybe default with self-signed certs. So we are going to specify the endpoint here, the public address, and then nil for the alternate DNS, and then alternate IPs. We know that we can specify the localhost IP. So net dot parse IP 127.0.0.1, and it returns an error if error is not equals to nil. In that case, we are just going to return nil, comma fmt dot error f, error creating self-signed certificate. Okay, so now that we have the self-signed certificate generated, we are going to create the new recommended config. So server config equals to generic API server dot new recommended config, and we already have the codec. So let's call it generic API server. Okay, so once we have the server config, what we are going to do is we are going to call k.recommended options.apply to, and then we are going to pass the server config. And apply to is the kind of the place where the magic happens. When I say the magic happens, what I mean is this particular logic is implemented. That is getting options from config. So when we run apply to, if you see here, for every option, if you remember, we called new recommended option. So we have etcd secure serving, etc. For every field there we call apply to, and then we are passing the kind of config, and we are passing the reference so that the config can actually be applied, and we get the config from the options. So in other words, apply to is the main function where the options, recommended options, are converted into the config struct that we have. If error is not equal to, let me note it this down maybe. So this is where the options are converted into config using apply to. So if error is not equals to nil, in that case we would just want to return the error, and then we can just return the cluster config and then nil. So all right, so now we have options and config. So if we look into this diagram, again, not diagram but this real rough document again, from config we need completed config, and that's what we are going to look into now. So we have the config, and we are going to have a function called complete that is going to give us the completed config. But before actually doing that, let's create the type for the completed config. So generic config, and it's going to be generic API server dot completed config, and the complete method on the cluster config is going to return completed config. And like I said, from completed config's new method, if we look into this particular type here, so there should be a new method that we are going to look into on the return type that would get us the server that we can run. So once we have the completed config, let's also create a type for the server. So cluster server struct, and it's going to be generic API server. Okay. And completed config. So we can just return so okay, so now that we have the completed config, what can be done is we can have new on this completed config, And that new, so these types are kind of just wrappers, and we have created these wrappers to enable us to maybe add new fields here, right? That's pretty much it. Otherwise, we are just working with the kind of uh, the standard or upstream types right now. So we are just working with, let's say, recommended config, completed config, and things like that. But we have these wrappers so that we can add new fields if wanted. So add new fields if required. So we are going to have a new function here called C completed config and new, and this is going to return the cluster server. But like I said, completed config dot new returns the server. So it's just kind of the yeah, I mean, semantic of how we are doing the things, but eventually we are just kind of calling the things on the types that are already provided. So it's going to return cluster server error. And here what we are going to do is we are going to, like I said, from completed config, we can call new. So c dot generic config dot new, and let's call it cluster hyphen server, and then delegation target, and delegation target is going to be new empty delegate. I'm going to talk about this in just a second. So if error is not equals to nil, in that case return nil and error, and then we can just return okay. So what's happening here is we are creating, so we had options, right? And from those options, we created the config, the cluster config. And once we have the config, we created the completed config, that is this struct. And from completed config, we got the generic API server, and generic API server is something that can be run. And as you can see here, it says that yeah, it's a runtime struct that can be run. So we have the cluster server now. This is the name of the server, and delegation target tells us once the request reached here, and let's say if this particular aggregated API server doesn't handle that request, should the request be transferred to another handler in the chain. Does that make sense? So for even for main API server as well as aggregated API server, we have a handler chain. And what it says is, if the request is not fulfilled till now, should it even be transferred to another handler, or should we just respond with 404? That's what this does. And it means that we are not registering any new handler. So now that we have this server, what we have to do is we can actually run that server. So let's go ahead and tie everything together in the options.go. So func and cluster server options, and under cluster server options we have run. It accepts a channel, then it returns an error. So now we are going to do the exact same thing that we just talked about. So we are going to get config by calling k.config. And once we have the config, we will have to get the completed config. So config.complete, and then using new, we can get the server. So server call, and these are the methods that we just wrote. So complete actually calls the complete from the standard type, and then things like that. So if error is not equals to nil, in that case we would like to return error. And once we have the server, we can do some other things. For example, we are adding the post start hook here, but I don't want to do that right now. I would just go ahead and run that server. So server dot generic API server dot prepare run dot run. So okay, now what? Yeah, this seems to be deprecated. We can look into this. That's not a problem. We can fix that later. So what we have now is we have an options type, and on that option, if we call run, what run does is it creates config from the option, completes that using config.complete, and once we have the completed config, we call new to actually get the server that can be run. I think if I not, yeah, maybe I forgot about explaining what complete does. So once we have options and config from options, to add the default values to actually complete the config, to add all the required default values, we call complete. So that's why the complete is actually necessary, I would say. So for example, if you see here, if feature gate is null, it adds the default feature gate. Like I said, it initializes, it adds the, let's say, sensible defaults to the config to make completed config. Okay, like I said, so now we have run. So all we need to do now is we need to create, like I said, initially, I think I briefly said that we would eventually like to just create a command line tool that can be run and accept some values. So that's what we are going to do now. We are going to create a file here, or let's say, let's just do it in options. Yeah, if you want to, you can have a new file where you can introduce this command, but I'm going to just add this, or let's maybe create a file called cmd.go, and here I'm going to write this new function called new command start cluster server, and this is going to return the cobra dot command. Now, I hope this makes sense, because what it does is, if you have the kind of the logic implemented, but you need the binary, or the command line binary made. So for example, if I want to call it cluster API, you need this binary to be made, so that you need this CLI to be made so that it can be called something like this. So etcd endpoint, abc, and then hyphen cube config, and things like that. So that is the reason we are going to create a cobra command. So what it accepts is, it accepts the default options, the options that we just talked about, cluster server options, and it also accepts stop channel. Okay, and once we have those two things, what we are going to do is, we are going to create a local variable from defaults, and then we are just going to, so if you search for Cobra Golang, it's just a kind of, yeah, a tool that can be used to create Go command line tools, I would say, very, very easily. So that's what we are that's what we are doing here right now. run cluster aggregated API server, and then we are going to run this particular function. So return L. And now we have the options here. And like I said, in the options type, we have a method called run that actually runs the API server. So let's just go ahead and run that. So if error equals to o dot run, error is not equals to nil, then we are going to return the error. So we can also validate the options and complete them if possible, if required, but we are not going to do them for now. Like I said, it's just a very kind of bare minimum project that we are building, at least in this particular video. So once we have this, what we are going to do is we are going to create the flags equals to cmd dot flags, and then o dot recommended option dot add flags. And this is something else that I would like to highlight. So if you remember, when we were looking into new recommended option, we briefly saw add flags, and what it does is it just adds the etcd flag for etcd option into the Cobra command line tool. So if you go to add flags, if you see here, it adds that value. It adds the etcd server override. So this flag is now added to the command that we just created using Cobra. So that's what this particular command is doing. It is adding recommended options into the Cobra recommended options flag into the Cobra command line tool that we just created. I hope that makes sense. So now we have everything written, at least. Let's go ahead and try to create a new file called main.go that is actually going to run this aggregated API server for us. So let's go ahead and tie everything together. So func main, and main, what we are going to do is we are going to initialize the init logs, and then we are going to defer. You can read the documentation for this. I think it just makes sure that the logs are properly kind of written before the process terminates. Generic API server dot setup signal handler. Let's call it generic API server. And then we are going to create the options easily because we already have constructor for options. So server dot new cluster server options, and os dot standard out, s dot standard error. And once we have the stop channel and options, we can create the command. So server dot new command start cluster server. It accepts the options and stop channel. This is the same command, same function that we just wrote. And once we have the cmd, we can essentially just run it. So cmd dot flags dot add go flag set, and then flag dot command line. We are doing almost the exact same thing here as well. So if you see, we call add flags on recommended options. Similarly, we are calling add flag set, and it just adds some kind of standard flags to the command line tool that we are creating. For example, let's say if we are using, let's say, klog to log the entries, that utility might be expecting some values, so we are just kind of registering those. And if error equals to cmd dot execute, error equals to not null, in that case klog dot fatal error. And that's pretty much it, I would say. So now that we have the main, we can actually go ahead and run this. But before actually running this API server, what we need is we would need etcd to be running, and because we have initialized the etcd options using new recommended options, we can easily specify wherever the etcd is running using the flag to the command line tool that we have just created, and that flag was available in the command because we registered that using this particular statement here. So let's go ahead and try to run the etcd container first. So I have a command already. So I think this is the command. If you see, very standard command, name of the container is going to be etcd cluster. It's going to be listening on 2379, it's container image, and that is pretty much it, I would say. So I'm gonna hit enter, and we have the etcd running now, and the other container is for the local kind cluster that we have. So now that we have the etcd, let's go ahead and run our API server. And to do that, I am going to run this particular command. So run main.go, because our main file is main.go. And once we have the main.go, what we are going to do is we are specifying the etcd servers. Like I said, I mean, this should make sense at least a little now. Etcd servers is the kind of flag that is introduced by new recommended options eventually. So if we go to options, new recommended options, I'm almost sure that this is where that flag etcd servers is kind of introduced. We can maybe look into that later, but this is where, yeah, if you see here, etcd servers. So this is where this is how that was made available to us. So let's run this, and let's just see what happens. Okay. So this is a problem. I already faced this problem when I was working on the video. So it's on config.go 20. So config.go line 20. So complete, and then 755. So complete, and then 721. So if you see here, yeah, it looks like we have not specified effective version, and effective version is going to be crucial here. So let's go ahead and specify the effective version. So I think the video is already very long. Let's just go ahead and try to kind of solve this problem, and then we would wrap this up. So before actually calling the complete, let's initialize the effective version. So k dot generic config dot effective version equals to, we are going to use this compatibility package and get the default build effective version. So let's import this. And compatibility.default build effective version. Now let's briefly go ahead and talk about this, because this is kind of important piece of code here. So what happens is, nowadays the Kubernetes API servers are kind of written in such a way that they can emulate a specific version. So for example, even if I have written, let's say, the Kubernetes API server or any API server, aggregated API server version with version, let's say 1.35.0, but I can configure my API server to emulate or mimic or pretend to be another version. So even if my actual version is 1.35.0, I can pretend to be 1.32.0. And let me tell you why this might be required. So let's say if you have a huge cluster and you are trying to upgrade some components of the cluster, and let's say, again hypothetically, let's say kubelet is trying to, you are trying to upgrade kubelet, and then there is main Kubernetes API server, and while upgrading, the compatibility is somehow mismatched, and because of that things might break. So let's say the main API server is in 135, so and kubelet doesn't support 135. So what main API server can do is it can pretend that it's in 134 that is supported by kubelet, so that the upgrade can happen smoothly. So I have not tried this, but I read about it, and that's what I kind of understood. So let's go ahead and try to run this again, and let's see what happens. Okay, all right, so here we go. Now, this is the kind of thing that we were, that I was looking for, serving securely on 9443. And if I go ahead and just uh, try to curl local host colon 9443, here we go. We see the version now. And if we query health, we also see the health. And eventually we would like to run this particular command, APIs, because APIs returns all the APIs that are registered, that are available in the API server. uh, so this is the standard API server that we were able to write, and I would like to get this command working, and let me tell you why. When we run kubectl API resources for the main, to figure the main API resources, that's the endpoint that gets called. So if you see here, this is the endpoint that gets called. So this is from the main API server, right? And we are writing the new server. So I would like to query the same endpoint to see what are all the APIs that are registered in the new API server, because this curl command that I'm making, this is not going via the main API server. The things that are happening using kubectl, they are going to the main API server, but this curl is directly talking to the aggregated API server that I have written, and is running on localhost 9443. So yeah, I think this is pretty much it, about what I wanted to talk in this particular video. If you liked it, like the video, like if you liked the content, like the video, and I will see you in the next one. Thank you so much.